Now we can talk a little about the LCD controller or the liquid crystal display controller. LCD displays are liquid crystal displays. They are very useful in displaying information, and they can give very usable and readable displays. Modern LCD controllers also include touch connectivity, by which these displays are also acting as an input device. Normal LCDs are only output devices, but touch LCDs are also input devices as well, because they are touch sensitive, right? So the classical LCD controller follow the HD44780 interface, which is a Hitachi standard HD44780 interface, and in that basically what we have an 8-bit data bus followed by an enable bit, followed by the read/write signal, and followed by the register select signal, and these are connected to the LCD controller, right? So basically this forms the communication bus of the LCD controller with a particular microcontroller. So this is how basically the things can be done. And we can see basically that we have the R/W line tells us whether we want to read the LCD controller or we want to write to the LCD controller. Okay, and enable is used to enable the LCD. Whenever we want to have the communication with the LCD, we would have to enable the LCD. And of course register select would select whether we want to write data to the LCD or we want to write the control information to the LCD. So whatever we want to display on the LCD would be decided by this RS bit, right? If this RS bit is 1, we are writing data or displaying the data, and if RS is 0, we are writing a command to the LCD controller. That is basically the idea. Okay. So there are some commands. If RS is 0, we are selecting the command option, right? And this R/W is 0, so we are writing 1/0, and so if this R/W is 0, we are writing to the LCD controller. This is the command that we want to write, given by data bits 0 to data bits 7. And what is the command? Clear the display and return the cursor home. Similarly, this is the command for only returning the cursor home. This is the command for moving the cursor to a particular direction. This is the command to turn on or turn off the LCD display or blink the cursor at the position, and similar to this. Now this is over here, this RS bit is 1, so we are writing data over here in this particular line. Okay. So these are basically the codes. I/D equals 1, cursor moves left. Similarly, I/D equals 0, cursor moves right. So we can position the cursor, right? So this is I/D. So we can set the different commands over here. So using this interface, we have this sample code, void write character C, right? So when we want to select write the data, we know that RS should be 1. So RS is set to 1. And whatever character we want to write is placed on the data underscore bus lines, which are DB0 to DB7. Right? This would be connected with the microcontroller's 8-bit port, right? So this would be an 8-bit port. To the microcontroller, which would be connected to DB0 to DB7. So after writing the character and after specifying that we want to write the character, we set the enable LCD 45, right? So this enables the LCD for 45 milliseconds by toggling the LCD with the appropriate delay, right? The E would be set to 1, then the timer would be counted for 45 milliseconds. Afterwards the E should be equal to 0 to enable and then disable the LCD display controller. There is another type of display that is called the LED 7-segment display. LED 7 segment displays, as the name says, light emitting diodes, right? So these displays emit light. So they are very useful in low light situations where they can provide very elaborate and very bright displays. This is in contrast to the LCD displays that are a little dimmer and they need backlight in order to make the LCD visible. Anyways, the LCD 7 segment displays are called 7 segment because they have got these segments A, B, C, D, E, F, and the center segment is G. And these can be common cathode or common anode displays, right? So basically, this is the common point, common line. If you want to turn the LED, this LED on, if this C is 1, then this LED is on. If this C is 1, then this LED is on, right? So basically, what do we mean by that? We can multiplex or time multiplex these displays. If we have 2 digits to display, one of the methods would be to power the 2 digits separately, right? For example, if we want to display a 1, we can turn segment B on and segment C on, right? On this display. And if you want to display a 2 over here, A, B, G, E, and D. So that would display a 2. So one of the ways for displaying 12 is to power this separately and display a 1 over here, and power this separately and have a 2 displayed over here. But there are 2 disadvantages. One of them is that the power consumption is a lot because this plays on all the time and this displays on all the time, display A and display B. So one of the less power consuming options is to time multiplex these displays, right? To quickly switch one display on, one display off, and then switch this display on and this display off. So at one time display A is on and the other time display B is on, and this pattern keeps on repeating. So this is called time multiplexing. And the obvious benefit is that power consumption is reduced a lot because these 2 displays are not on all the time. They are on basically for a certain chunk of time or a certain period of time. So how do we do that? These are the segment lines A, B, C, D, E, F, G. We make them common. So if we supply a 1 or high input on segment A, this segment A is also provided with the high input. So what would we do? We can display a pattern over here, turn this LCD on or LED display on, then we can display a pattern over there and turn this LED display on. So if we want to display 12 in this scheme, we'll first send the code for 1, which is B and C are on and all other segments are off. So we supply a code of 1 and we turn the display A on and we turn the display B off. So 1 is displayed over here for a little short period of time. Let's say 10 milliseconds or 20 milliseconds. So after 20 milliseconds, what do? We send the code for 2 on this and now turn display A off and display B on. So this pattern of 2 is displayed over here. So if we repeat this process, pattern of 1 is displayed over here and pattern of 2 is displayed over here. So according to persistence of vision, we see that 12 pattern being displayed. So this is basically the thing. If we want to reduce these lines of the microcontroller even further, we can have a BCD to 7 segment decoder. So we supply only 4 BCD code, 4-bit BCD code, and it is automatically converted to 7 segment code. What do? We will send 0001 first to over here. So the code of 1 would be supplied on these lines and this display A would be turned on and this display B would be turned off. So 1 would be displayed over here. After let's say 20 milliseconds, we supply the code of 2 on the BCD code of 2. So the pattern of 2 appears over here. Then we turn display A off and then we turn display B off. So pattern of 2 displays over here. So in this approach, we can decrease the lines even further to just 4 lines to controlling the display. Another beauty of this scheme is that we can increase the digits being displayed without a very large increase in the number of control lines required. So this is called time multiplexing of 7 segment displays. Now let's look at an example of interfacing an LCD to a microcontroller, right? So what is the problem statement? We want to interface a 2-line 20 character LCD module, 2 lines and 20 characters per line module with the built-in HD44780. Remember, I told you this is the standard HD44780 controller to the IO ports of the PIC18 microcontroller. So we are using a PIC18 microcontroller and we want to interface this LCD with the PIC18, right? First of all, the most important thing is that the LCD module has got a very important connection, which is VSS is ground basically, and VEE is the contrast of the LCD. So just make sure that you connect this variable resistor to this contrast of the LCD so that you can check, right? You can make the maximum contrast and you should see this particular pattern where all boxes are displayed. If all boxes are not displayed, black boxes are not displayed and using this contrast control, it means the LCD is bad. So this is the first thing that you should do, right? These are the RS, RW and E lines of the interface, and these are the data lines. All these lines would be connected to the microcontroller's IO port. So converting to ASCII, the LCD can represent characters in ASCII, right? So we will display the ASCII code of the particular character. So we want to display number 8. So the ASCII code of 8 would be 38. So 38 would be output. That is the idea. Okay. And so on and so forth for different characters that we can have. So in order to interface the LCD, the hardware is basically a 20 into 2 line interface, 2 lines with 2 characters per line. And as I told you before, this VEE line is connected, which is an important connection for the contrast adjust. And basically these are the R0, RD0, RD1, RD2 and RD3 lines of port D, and this is the RA1, RA2 and RA3 lines of port A. So RA1 becomes E, RA2 becomes R/W and RA3 becomes RS. Okay. So LCD has displayed data RAM, right? The display data RAM is there, which is used to display the characters. This is all memory mapped, and each register in data RAM has its own address that corresponds to its position on the line. So we don't need to go to such high details of this line, but we just want to remember that address range for line 1 is 00 to 13H and line 2 is 40H to 53H. So 0 to 13H would be the address ranges for the first line, and 40H to 53H would be the address range for the lower lines. Okay. So how do we interface the LCD? First we connect the line, the pin lines, right? RS of the LCD is connected to register select RA3 of the PIC microcontroller. R/W is connected to RA2 line of the microcontroller, and E is connected to RA1 line. So power, ground and variable resistor are connected. Like I told you before, this is the internal structure of the HD44780 module. So how do we write the code? The code basically begins with defining the lines. It is always a good idea to define all the lines using defined directives, and do not hard code any line into the code itself. Okay. So we can, the beauty of this approach is we can just change the ports at the top, and that change would be automatically adapted to all the line of the particular code. So E is defined over here, RW is defined over here, RS is defined by this port. Okay, so we define the address bus, which is defined as port RB. So define instant is defined as 1, right, and data is defined as 2. Instruction is defined as 1 and data is defined as 2. So what we have, basically we have a function output, which is in which we define a character, and we also define a character representing whether it's an instruction or it is the data, right? So if this is 2, then data is specified. If this is 1, then instruction is specified. So we check if instruction, if this byte is data which is 2, it means data is to be written. And for data, I told you before that RS has to be 1. So we set RS to 1. Else we set RS to 0. And then we set RW to 0 for writing, right? And data, we place the character A on the data bus. We enable the LCD, we delay for 5 milliseconds, and then we disable the LCD to complete the writing process. So we can have, of course, LCD.cpp main, we can output H, right? We're putting H on the display, and we can output C to send the command C. Okay. So right, when we were outputting, we were calling the output function, right? So in output function, if you are printing a data, we'll specify it with the data, right? And then if we are providing a command C, we'll provide what byte over here? The INST, instruction byte over here. So this is how the thing works. So interfacing the LCD can be interfaced either in the 8-bit mode or the 4-bit mode. 4-bit mode is a low line version in which the data bus is not transmitted in 8 bits, it is transmitted in 4 bits. So in the 8-bit mode, all 8 data lines are connected, but in the 4-bit mode, only 4 data lines, DB7 to DB4 or DB0 to DB3 of the LCD are connected to the microcontroller or the controller device. And the driver is HD44780, which has 2 internal registers, instruction register and the data register. All instructions are held in the instruction register and all data is held in the data register. So this is basically the commands. Like I told you, all commands RS would be 0, yes or no, and R/W would also be 0 because we are writing a command. And this is the command. Command 1 is basically clearing the display, and the execution time is provided, right? So you can time set displays after the particular thing, particular command. And these are the commands that are continued for this particular HD44780. So if you want to interface the LCD operation, when the microprocessor unit writes an instruction, the controller sends the data DB7 high as a flag to indicate that the controller is busy completing the operation. Okay. So sets the data line DB7 low after completion of the operation. So we can check DB7 to find whether the operation has completed or not, or we can just have a timing of the arrangement. So the MPU should always check whether DB7 is low before sending an instruction or a data byte. So you can check by reading the data, the status of the device and checking the DB7. If DB7 is low, it means that the controller is ready to accept the next data or a command. If DB7 is high, it means we have to wake. But you cannot check DB7 just after power up. After initialization, then the DB7 effect is actually come into play. So how do we, now we can describe how we can write the data to the LCD. This is also already been shown. So the microprocessor unit would send RS to low to select the instruction register. All instructions are sent by RS equals 0. You can read the LCD by asserting the read write signal, right? It can assert the enable signal high and then low to latch a data byte or an instruction. This is just similar to the command that we discussed before, right? The pattern. Remember? Right? First we selected the RS according to whether it was an instruction or the data. Then we send RW to 0 because we are outputting or writing. Then we place the data to be written on the data bus. Then we set E equals 1. Then we waited for a time and then set E equals 0. This is called toggling the enable line. So the same instructions have been provided, right? RS is selected LCA, the r/w line is selected, whether you are writing or whether you are reading, right? And then it toggles the data byte by sending thing. And if we want to write data, we set rs to high, and to select the data register, we write into LCD by setting the r/w signal. So this is basically the timing diagram. So we need not be very concerned about the bus timing of this particular device, because we are already converting basically from that thing. But nevertheless, rs should be executed first, followed by r/w, and whenever enable is selected, then only the data bits would be sampled by the LCD module. So that is the main idea over here. So interfacing the LCD, for writing the software to write into the program should send the initial instruction. Yes, the initialization of the LCD should be performed first. Then the DB7 should be checked until it goes low. Then of course we can write instructions to the IR to set up the LCD parameters. This is called initialization, and then we can write data to display a message. So first the initialization should be performed, then the other commands of the LCD should be taken place. So this is the sequence for resetting the LCD. We will wait for about 20 milliseconds first. With the first value is sent, first command is sent, 10 millisecond wait. Second command is sent, 1 millisecond wait. Third command is sent, 1 millisecond wait. And then we set the parameters, and then we wait for 1 millisecond. So after we perform these steps, we properly initialize or reset the LCD. And this is the LCD init code as it has been shown, right? And we first delay 20 milliseconds. This is the first initial line, 10 millisecond. Second sequence, 1 millisecond wait. Third sequence, 1 millisecond wait. Then we initialize properly, and then we wait for 1 millisecond. So this is the proper LCD initialization code that we can have.